Okay, thank you very much, Corentin, for the invitation. Very happy to be here. So as Corentin mentioned, I'm coming from physics, and for the past about 5 years, I've been thinking about theory for chemical reaction networks, and that's what led me into this topic that you'll see here today. Okay, so let me start from a few general motivations. So at the risk of Corentin was saying, well, in biology, it's difficult to use biology as a singular, but let me at least draw some general motivations from biology at large. So one very strong one is, where does agency come from? At the scale of the organism, we're used to talking about biological organisms with the language of agency. The predator tries to catch prey, the bird builds a nest for its future young, and so on. And since the advent of video microscopy, we see this language creeping to smaller scales, although it's somewhat more controversial to apply it there. So there's a video here many of you will have seen.
This classic movie was made by David Rogers at Vanderbilt
blood cell chasing
in the 1950s.
Some little bacterium.
It shows a neutrophil.
And it's hard to watch a video like this and not try to apply some agential language to it. Another example I mentioned is work by Michael Levin on limb regeneration, where one wants to say that the organism decides to grow an extra leg or decides to grow an eye. It's quite natural to use that language, but how is it justified? And in particular, where is the dividing line between some reductionist description in terms of chemical reaction networks, Newton's laws, and so on, and some agential one, if one actually exists? So in particular, if everything in biology has some ultimate mechanistic description, how does this not conflict with the agential descriptions? And this is really a problem of dualism. I like the coinage by Levin and Watson as an agency body problem, because these are really two very different ways of looking at something. And unless we actually throw out all the agential language entirely, we have to somehow reconcile these. And it seems that in modern work, the tacit solution is that agency is emergent, but then how does it emerge? What is the mechanism? Emergence means that surprises happen, but it doesn't mean that anything goes. So we should have some mechanism for that emergence. Now, a second motivation is, how should we think about noise in biological systems? So we have, from everyday connotation, this connotation of noise as a nuisance, audio noise, visual noise, the signal versus the noise, and so on. And there are certainly cases when that is the right connotation. So anytime you want to fix some concentration of some molecule, then by definition, anything that deviates from that is harmful. And there's also applications where you want to convey some message. So it could be by chemical means or by a sensory system or something. And also it's quite natural to think of noise as detrimental in that case. However, by now, over the last, say, 25 years or so, there have been an increasing number of examples where noise is really facilitating some behavior. So there are noise-induced transitions, like switches in epigenetics. That's what I'll discuss later in the talk. Also, Brownian motors or ratchets. In other cases of, for example, non-genetic heterogeneity that can be used as bet hedging in some environment. And so in all, say, these latter examples, the explanation for what's happening usually says, okay, it's surprising that noise can do this and do that. And when you find yourself saying that something is surprising over and over and over again, it means you're probably thinking about it in the wrong way. So is there some way that we can understand both of these rules of noise in a coherent fashion? Okay, so that's another question that motivated me. Okay, so let's get into it. So I know that there's a variety of folks in the audience, and things will not get too technical, but please, if you have questions, just drop a line in the chat, and I'll try to track everything as we go. Okay, so let me start with Langevin theory, what mathematicians would call stochastic differential equations. Physically, it's just evolution of some state where you have noise on top of it, okay? So a classic equation would be something of this form. dn dt is some function of n plus a noise term. So n would be the state of your system, and c would be some white noise. So there are different examples where this could apply. It could be over-damped motion of some molecule in a solvent, for example. In that case, n would correspond to position. F of n would correspond to the deterministic forces, some dimensionless way. And c would correspond to the random kicks from the environment. Then in that case, the noise strength would be proportional to the square root of temperature in that example. Another example would be a chemical reaction network in the regime where the populations are large but not infinitely large. In that case, n would correspond to a molecule count. F of n would correspond to the terms you get from the reaction rate equations, the deterministic dynamics. And c corresponds to random noise that you get fundamentally because chemical reactions are random events. So that's called population noise in this context. And in that case, the noise strength goes like the square root of the population. In this talk, you can really have either in mind. It's not so crucial. It actually might be a bit easier, say, in the first, to have the first example in mind, but it's not really crucial. And the formalism does not, all the things that I'll tell you really apply to both cases. Okay. Now, totally separately, let me say a little bit about control theory. So in control theory, one has some evolution equation where, again, you have something that's a state. But now what you have is a control. And a control problem is to choose the control to satisfy some objective. So very often it's to get the system from one specified state to another specified state. And an optimal control problem is to do so while minimizing some cost function that we don't really need to specify. Okay, and what I want to emphasize about control theory is that there's two things. First is that choosing requires the ability to search the space of possibilities, even if it's only mentally or by some modeling. So the usual case in engineering, and say in synthetic biology maybe, is that the engineer is choosing this based on some model, at least a mental model, if not an explicit mathematical one. And so in that case, it's really an external control. However, if we want to think about how control theory is used by biology in vivo, which is what I'm interested in, then that's not applicable anymore, and we need to think of other ways to do so. So one way is, okay, something could be evolved. So in other words, it's being searched over evolutionary timescales in some discrete fashion. Or it could be due to timescale separation. So for example, if your control variable has its own dynamics, but it's much faster than the x dynamics, then the x is essentially fixed while u is doing some exploration. And it's possible in that case that you can search the space of possibilities enough of a way to satisfy some objective, to solve a control problem. So really, it has to be very chaotic to do so. So then the question is, okay, what mechanism does biology use? Or maybe more precisely, under what circumstances does it use? One, say, evolution mechanism, under what circumstances, another one. And a second note that I want to make is that control theory defines a notion of agency, and a very, very powerful and general one, because the agent is whomever or whatever selects the control. And if the control achieves the objective and isn't zero, then by definition, the system exhibits goal-directed behavior. And I would argue that this is a very, very practical notion of agency because it's the one that engineers use whenever they want to solve problems where they have some goal that needs to be solved by a machine. Now, okay, if I return to the Langevin equation for a minute, writing it down again here, let me make things a bit more precise. Let's consider a transition probability to go from one specified state to another. Then, so for example, as in the picture here, I could have states going from, trajectories going from one state, the local minimum here, to another one that you can't really see. A variety of them are shown. The different trajectories will be weighted in a different way. If you have white noise, what that means is that your trajectories will be weighted with e to the minus s, where s is basically the time integral of c squared. Now, it's not hard to show that in the weak noise limit, so when the noise strength is small, the dominant trajectories are those that minimize s. And so for the first example I gave of overdamped motion of say a particle, weak noise corresponds to small temperature. For chemical reactions, weak noise corresponds to large populations. And now if I put it side by side with the control problem, you can see that these two things, in the weak noise limit, they're actually mathematically identical. So there's a mapping between optimal control problems, where you're minimizing some cost function to get your state from one specified state to another, and what happens in the weak noise limit in a stochastic system, where the noise plays the role of the control in these dominant trajectories. So this mapping has been known in the mathematical literature, so in what's called the large deviations literature. And it's been used as a mathematical mapping, both to take results from one field to the other, and also to, say, prove that certain algorithms for numerical computation of these dominant trajectories, that they converge and so on. So it's been used for those purposes. And one consequence of this is that the mapping implies that optimal control problems can be solved by stochastic systems. So let me illustrate this. Okay, I should say this was discussed a lot by Kaplan in a series of papers. So let me illustrate with a problem not coming from biology but at all, but one that's very interesting, as I'll describe. So this is the Goddard problem. It's to find the maximal height a rocket could go with a given mass of fuel. So in that case, the state is defined by the vertical velocity and height of the rocket and its mass. And the control is the thrust as a function of time. You can choose how much fuel to use at each instant of time. And there's some maximum thrust that you can do. So this is quite interesting because naively you would think, well, I don't want to carry fuel any higher than necessary, so I should just burn the fuel as fast as possible. However, once you take into account drag, that's not true anymore because drag increases the faster you go, so it might be worth carrying fuel up to burn it at a slower speed. And also the atmosphere gets thinner as you go up, so it might be worth carrying fuel to burn it in a thinner atmosphere. And it turns out the optimal control is highly non-trivial. It took 50 years to solve this problem. It turns out the optimal control, so here I'm plotting a few things. The red is the control. It turns out the optimal control has 3 stages. There's a first stage where you do go full throttle. You burn the fuel as fast as possible. However, at a certain stage, it actually becomes optimal to change discontinuously to some lower thrust, and there's a very non-trivial curve specifying the thrust as a function of time, until at some point you run out of fuel and then you just coast to your final height. Okay, so that's the optimal control. It's very generically, it has this 3-stage form. Now, as I said, by virtue of this mapping, one should be able to solve this with a stochastic system just by taking these equations, and instead of using U as something that's externally found, by making U random noise. Okay, so what I did is I just sampled 1,000 trajectories of this system, and the middle one shows you the best trajectory, so it's the one that gets the highest. And on the right is some more typical trajectory at a certain value of beta. So I sampled paths with this form here. I'll return to that in a second. So what's very cool is that these are just sampled randomly, but the optimal one, the best one that I found, it happens to have a large drop that's very near where the optimal control has a large drop. There's, of course, other stuff going on top of that, but as a result of just happening to get this large drop, then you get, say, within 10% of the maximum height. On the right, this is a more typical path at beta equals 5. So that means that the strength of the noise is about 0.2 in dimensionless sense. And you get about 20% to about 20% of the maximal height in that case. So, okay, this may not be a very efficient way to solve optimal controls numerically, but the point is nature is simulating stochastic things on its own, right? That's what nature does. So let's go back to this noise control mapping in general and ask, okay, how was the weak noise limit actually used? It was really only used to get optimality of the control. And what I want to argue is that this mapping is not just a mathematical or numerical tool, but it actually has physical meaning even beyond the weak noise limit. So in particular, that we can always consider the noise as a control field. And that's what I want to explore. So let me note that the noise can have different sources. So if the noise is intrinsic, if it's population or demographic noise, then one might call this an endogenous control. And I think this is a concept that lacked definition that could be relevant in biology in particular. If the noise is external, for example, from the medium, then one might call it an exogenous control. Now, in either case, it's distinct from the usual scenario in control theory where the control is free and imposed externally by the engineer. So in either case, it's really nature automatically sampling different control trajectories. So actually the distinction between these two cases is not so important, actually. At least for what we'll talk about today. Okay. Let me just check to see if there's any comments. No. Okay. Okay, so now let me develop things in a little bit more detail. And the way that I will do it is to start from a path integral formulation of stochastic systems. So a lot of big words, but it's nothing scary here. It just means for a stochastic system, you can write any probability or expectation value as a weighted sum over paths. So just like as I sketched before, if I have a bunch of paths from one point to another, it turns out you can write any observable you might care about as some weighted sum over these paths. Okay, the actual technical details of this, they depend on whether you're starting from, say, a Langevin equation or from a real chemical reaction network and so on. But I'll skip over all those details here. And I illustrate things with the Langevin case, okay? Now, as I said before, in the weak noise limit, okay, as you might expect, one or a few optimal paths dominate. And it's conventional to call these instantons. These will be exactly like the optimal controls that I mentioned. And importantly, they're not random objects anymore. They follow deterministic equations, although they turn out to be acausal equations. So the equation for the instanton in a Langevin equation, the first one here, well, this just looks just like the original Langevin equation, except here, this is just a kind of modified version of the noise. And this new variable pi that's introduced, it has many names in the literature, momentum, tilt, very vague names. It turns out its equation, it has its own equation of motion. It must be solved backward in time. So this is always quite obscure. And as I was teaching myself these methods, the question that kept popping into my head is, what is the physical meaning of this pi field? That's actually what led me down this whole path. Okay, but by virtue of what I told you before, it's natural that this pi field is actually a control. And that then explains why it must be solved backward in time, because in order to reach a desired final state, we must choose the control appropriately. If I don't choose the control appropriately, I will just get to some other state that's not the one that I want to get to. And what that means is that if we think of this, that we can ascribe the paths a physical meaning, that by noise, nature is constantly exploring possibilities. And we can think of that as attempting control. It's the same thing. And another way of saying that is that noise both has a kind of incoherent part, which is what we usually think of as noise, and it has a coherent part, which is described by these instanton equations. Now, the main effect of this coherent part is to achieve hops between attractors, okay? So for example, like switches. So if I take a system that has, say, two wells, and I simulate it and look at its position versus time, you see a typical curve like here. The blue splotches are when the particle was in one well and it's just jiggling around under the thermal motion. But then rarely it has these hops where it hops over to the other attractor. And those are the really thin vertical lines. Now, what's a bit abstract about this interpretation is that our knowledge of the hops is incomplete a priori. So what we can predict, it turns out, are transition rates, but not the times of the hop. So if we take a trace like this, I can predict the rate at which transitions will happen, but not the exact times. And that means in particular that I can't partition the noise into these coherent and incoherent parts until after the hops have occurred. Once you have a trace like this, then you can do it. Now, this is a bit abstract, so let me offer two different analogies that shed light on different aspects of this. So the first analogy is with the emergence of dissipative behavior itself. So the scenario that you consider in the first thermodynamics course is to consider a dissipative system like a gas in contact with some reservoirs. And if you take such a system, you can model the individual molecules with Newton's laws and interactions that are fundamentally non-dissipative. However, the emergent behavior that you get at the large scale, thermodynamics, is really dominated by dissipation. And there's no contradiction, because in real life, when we apply thermodynamics, we're applying it to systems that are really approaching thermal equilibrium. They always start with some special non-equilibrium state. And so we have two different ways of looking at the same system. They look very different, but that's not a contradiction. And more importantly, the microscopic description in that case is really more complicated precisely because it retains this microscopic so-called conservative behavior that's absent macroscopically, okay? So what is the analogy? Well, here we're starting with a dissipative system where everything is causal. So I have this white noise, it has no memory, it's just trying things randomly. However, over long time scales, you get emergent behavior that is agential and acausal. So it has goal-directed behavior and the trajectories are not causal anymore. Again, there's no contradiction because this is only over the large scale where we start to see this agential behavior. And moreover, the full description, which would include both the coherent and incoherent parts of the noise, is more complicated precisely because it retains this microscopic causality. Okay, so I think that's one analogy to shed light on some of these perhaps counterintuitive aspects of what I'm saying. As a second analogy, I can make one with quantum mechanics, which, okay, some of you will know from your education or just the general culture. So the quintessential experiment of quantum mechanics is the double slit experiment. You shine electrons through a first screen that has two slits in them, then record arrival of the electrons on another screen. And even though you can record the arrival of individual electrons, the pattern that you get here has an interference pattern, which is more characteristic of waves. So this is the basic phenomenon that's very hard to understand intuitively. And what we know from a century of study is that if you try to force an interpretation of quantum mechanics where you can ask which slit the electron went through, it just leads you down into a huge mess. So it's really forbidden to ask which slit the electron went through. Okay, and the analogy that I will make is that here we have this agential behavior, we have goal-directed behavior, but it's forbidden to ask exactly when the hops will occur. Okay, that's something you can only figure out after the fact. Okay, so those are two analogies. You can take them or leave them, but I think that they shed light on some aspects of the behavior here. However, this is all still a bit abstract, so let's see everything in a very concrete, simple example, okay? And what I will consider is the example of a double well. If you want a biological example in mind, you can think of a toggle switch, and for certain parameter regimes, this system will have two attractors, either where X1 has a high concentration and X2 is low, or vice versa. I'll give the references later for this computation of the hops in this actual example. What I'm showing you are results from a much simpler example, but qualitatively that has the same physics. So I'll show you results for double well potential, where I just arbitrarily labeled one of these states off and one of them on, and we'll consider a hop from off to on. Now, you can compute what is the optimal control in this case. And here are different curves. H just parameterizes how long the hops take. Let's just focus on the lowest curve here. So say the red one, which is the hop that takes the longest time. Now, the form of this, it takes exactly the form of the force that you would need if this was a particle in this well in overdamped conditions. What you would need to push the particle over the hill. So you imagine you start in the off state, you start pushing. Well, you have to increase your force as the slope gets steeper, and then once you get to the top, actually you can just let it go and it will glide freely. So the magnitude of that force is really exactly what you see as this pi of x here. And a bit more precisely, it's the form for a given total time of the hop that minimizes the force squared in that case. So I think it's very intuitive what this pi means once you realize that it's a control. Okay, and even though this potential is fully symmetric in space, the optimal control, pi of x, is not symmetric in space or time. So it's agential and it's acausal. It knows about, it has a certain goal in mind, which is to get the system from off to on. It takes exactly the form to do so, given the constraints of doing it a certain amount of time and minimizing this force squared, okay? And okay, so what's lacking in this example, though, is that there's no imperative for the system to go from one state to another, for example, as a response to forcing. So if you simulate this example, what you'll get is a trace like what I showed you before, that the system will reside in one basin for a while. It will have these random hops, and each individual hop has this goal-directed behavior, but there's no overall large-scale function that the system is doing, okay? However, it turns out as soon as you add one more ingredient to this system, you start to get very interesting behavior. So let's now drive the system by periodically modulating the well. So we're going to modulate the depth of the well in some sinusoidal fashion. And the driving is weak, so it's not sufficient to actually remove the middle barrier, which means that any change in behavior must be mediated by the noise, okay? Now, if we think of this as an overdamped particle, the rate of hopping you can get from classic theory by Kramers. And the important thing is that the rate depends exponentially on this barrier height, delta V, and on the noise strength. So when the noise is small, the rate is slow because the transitions are rare. And once you have this rate, you get the typical waiting time of hopping, which is just 1 over the rate. So now what happens? So let me fix the driving period that I'll write as T drive and vary the noise strength. So when the noise is strong, which means the typical time to hop is small, you have many transitions hopping back and forth. You can kind of see the periodic signal buried underneath, but it's there in the background. In the opposite limit, when the noise is very, very weak, so the time to hop is very large, then you have these rare transitions, but you don't see any sign of the periodic signal. If you tune the system such that the time to hop is half a period, then you see this very, very strong entrainment of the system by the periodic signal. So this is a resonance phenomenon. This is, in fact, the famous phenomenon of stochastic resonance discovered about 40 years ago by one group in Rome and one group in Belgium. This later paper is a comprehensive review in the physics literature by 99. And so this is a resonance phenomenon. You tend to see hops in sync with the driving at a certain noise level. And in a certain sense, the ability of the system to enhance a signal, well, sorry, let me say that differently. The system can enhance weak signals by noise. And so the behavior with noise is non-monotonic. It's worse at high noise and it's worse at low noise. It's best in the intermediate regime. And there are different ways to look at that quantitatively. So one way is to look at the power spectrum of this is in log axes, this power spectrum as a function of frequency. The curve in the background is like the noise, but then you see this very sharp peak, and that's at the driving frequency. There's also some resonances at higher frequencies. And let me note that, so the essential point here is that you get this entrainment. So there's a preferred time to hop, which is in fact right when the barrier height is lowest. And this goes back to the fact that the rate of hopping depends exponentially on the barrier height. So it's very sensitive to changes in that height. And this condition that you get the time to hop exactly then, mathematically, you can obtain it just from action minimization. So physically, the optimality of the control is what's giving you the fact that you will choose to hop exactly at that most opportune moment. Now, there's a huge literature on stochastic resonance. There are many applications to apply, many ideas to apply this to biology. An early experimental demonstration was in the sensory system of the crayfish. They basically took a crayfish and they added some external noise and they tracked the behavior as a function of noise and showed that it was non-monotonic and in agreement with the stochastic resonance phenomenon. A more recent paper, the middle one here, it's from 2008. They review the history of attempts to connect this phenomenon to biology. There's a lot about neural behavior that I won't go into, but there are other discussions there. And then there are other papers where the connection's a bit looser, but for example, here by Poulsen, this is a study of a simple feedback motif in a reaction network where they note that the behavior is qualitatively similar to stochastic resonance. Here's a paper where they don't mention stochastic resonance explicitly, but the phenomenon also has kind of rhymes with stochastic resonance. Now, this cartoon that I showed you, it's from the review article. And actually, the way it's presented in the review article is here with these happy faces and sad faces. So it was already realized that it was natural to think of this in a kind of agential language, even though it was a bit ad hoc. So for example, when this right well becomes lowered, then the system is unhappy in this state and it will choose to hop over there. But given what I told you with this noise control mapping, we can just do this systematically. We can translate what's happening from a stochastic language to one from a control theoretic language. So from a stochastic point of view, the core idea is that noise helps the system respond more effectively to a weak periodic signal by enabling barrier crossing. From the control theoretic point of view, the system is using the internal fluctuations as a control strategy to synchronize. And the role of noise in the stochastic view is, well, it's an exogenous disturbance, whereas from the control theoretic point of view, it's control input. And it's steering trajectories towards useful outcomes. As I said, the minimization of action corresponds to the fact that you will choose to hop when the barrier is lowest. And overall, from the stochastic point of view, the role of noise, it seems kind of accidental, that you kind of accidentally exploit noise to improve performance. Whereas from the control theoretic point of view, the system we think of as actively leveraging noise as a strategy. Now, okay, so what I showed is that if you take a double well system, so basically the simplest system with more than one attractor, and you add this periodic driving, you already get this wealth of behavior. And it turns out if you add one more feature, you get a whole other wealth of behavior that's also relevant in biology. So if you take noise and time periodic forcing, that's what I showed you already, but now add a potential that's asymmetric in space, then you can get directional motion. So this is basically what a Brownian motor or ratchet does. There are different, many different examples in literature, different cartoons of this. One possibility is to have the time forcing be that you have a spatial potential that goes on and off due to some binding, like this. The asymmetry is that the spatial potential is asymmetric from left to right, so it's like it has a sawtooth form. And if you have these two ingredients, you will get directional motion. Now, to make the connection to stochastic resonance clear, let me consider a particularly simple form where this potential it's a sum of two parts. One is an asymmetric periodic potential, so like just the sawtooth that we have here. And now I'll add a time-dependent part that is just rocking the whole thing up and down. So like in this picture that I have here. And the effect of the rocking is to temporally modulate the barrier heights there. Now, this is almost identical to stochastic resonance mathematically. You can do the same computations, and you'll find, for example, that if you minimize the action, you will get the optimal time to hop, and you can work out what is the net movement that you get very straightforwardly, at least in the weak noise limit, and it's even easier under the adiabatic regime. So, okay, again, there's a huge literature on all this stuff, but the point is just taking noise-induced hopping and adding these extra simple ingredients, you already get this wealth of behavior, and wealth of behavior that calls for a agential description. So, right. So again, okay, since this is so similar to stochastic resonance, then what I showed you as the kind of mapping between the two essentially holds here, that again, you'll find that there's an optimal time that you choose to hop from the control theoretic point of view, and that's the key phenomenon that allows you this directional movement in this case. So there's a whole other discussion about this related to symmetry breaking and so on. That's more the physicist way of looking at it, but I'm trying to emphasize what I think is of interest to biologists here. Okay, so the double well system is quite attractive and illustrative, but it does have several features that simplify things. So the first thing is that in higher dimensional systems, the optimal path is non-trivial, even if you just have a small number of attractors, say 2. That's because the path itself, like, okay, in one dimension, of course, if you're going from one well to the other, I have to go over the hump. But in higher dimensions, I could have many paths that take me there. And in particular, the relaxation paths can be different from hopping ones. So for example, this is from this review paper for physics. The hopping path takes one path, the relaxation path down takes a different path. And that's related to distance from equilibrium and all kinds of stuff. But what's really interesting is when you have many attractors. So say if I think about a 2-well system as a switch, what happens if I have many switches? And think about this as, say, an epigenetic system. Then naively, you expect 2 to the n cell types, but one actually observes far fewer. So why? This again boils down to the fact that the hopping rate depends exponentially on the barrier height. So any small interactions with switches will favor certain paths over others and lead to dominance of a small number of attractors, which is similar to something in physics we know as a spin glass. And this was discussed a bit by this paper by Wolanis. But the really key thing, in my view, is that nature is automatically searching this space for optimal paths. So it's leading to these highly non-trivial optimizations in high dimensional space, essentially for free, just because it already has this Brownian motion built in. Okay, now let me make 2 notes relevant to this case once we have many attractors. So if we start to have a variety of barrier heights, well, then we'll have a variety of timescales. And you only will see the higher barriers on longer timescales. So control emerges over time. And you can figure out, okay, the time scale is related to the rate of hopping. If we write it in terms of control, the time scale depends exponentially on the amount of control. So the more control that is needed to get up to a saddle to cross into a new basin, the longer the time it will take to see those hops, and the longer time it will take to equilibrate between hops back and forth. So over very, very long time scales, you will eventually hop over all the possible barriers, and you'll start to have then an emergent jump dynamics over the attractors. This is discussed a lot in this paper here. And it's really the rates of all those hops that will be optimized. Okay. So a natural question from that is then, does this imply some kind of global optimality principle, which has been for a long time the kind of dream of what can happen in non-equilibrium systems and in biology in particular? So in what I told you already, the optimal control problem is defined for a given transition probability. So I fix two states, and I can find there's a certain optimal path that will take me there. What happens if we can consider some other observables? So let me consider, again, a two-well system initially, but maybe not necessarily in one dimension. So this is just like some cut through the system, as illustrated here. If W 0 to 1 is the transition rate per unit time to do that hop, then okay, over a short time, the total transition probability is like t times that, because okay, I can hop at any time and I can hop over. But over a short time, I'm not likely to hop back. But over a long time, well, I'll start to hop back sometimes. And actually, if I wait long enough, I'll forget where I started, and all that will matter is the relative rate of hopping back and forth. So over a long time, this probability depends on both of these transition rates. And so that means that just maximizing these rates by choosing optimal paths does not necessarily maximize or minimize this P here. And once I have many attractors, the dependence of long time transition probabilities on the individual transition rates is very complex, even in the long time limit. Okay, unless you have detailed balance dynamics in which you're back to equilibrium physics. So it means that you don't easily get a global optimality principle just from this local optimality of transition paths. However, you can find observables that would be optimized. So if I take some observable where the C's are some positive constants and F is some increasing function, well, then optimizing all the W's will optimize this theta globally. So for example, if F of X is X log X, and all the C's are just 1, this quantity here will be maximized. It looks a little bit like an entropy, but it's not exactly, because the transition rates, they're not normalized in any way. So this is actually not an obviously meaningful quantity. It looks a bit like the entropy production, which has this W log W form, but entropy production involves the difference between the correlation between the rate in one direction and the rate in the reverse direction. And optimizing the W's tells you nothing about that optimization about that correlation, sorry. So it's really not related to entropy production. And another idea, which comes from Bialik's group, and Gasper Kacek was the lead author on these works, is to consider gene regulation as a kind of input-output device, where the input would be concentrations of transcription factors, and the output would be gene expression levels. Then from the information theoretic point of view, you can quantify the efficiency of regulation by measuring how much information you learn about the input from measuring the output. And that's quantified by what's called mutual information, which is written in a certain way in terms of probabilities. And in this first work, what they showed is that from data on the fruit fly embryo, this mutual information is maximized to within 10% of an information theoretic maximum by what they measured. And I will just note that, okay, and later it was proposed, well, maybe maximizing information flow was like a design principle of biology, that this was something that evolution has sought. And I will note, okay, you can write these joint probabilities in terms of some conditional ones. Each of these are transition probabilities, and these look this again looks a little bit like what I showed you before, but we have these other factors that are present. It's a bit more benign than in the entropy production case, because these P of O and P of I, they're more integrated observables, so they will be less sensitive to fluctuations. But again, we don't get any exact optimization of information flow, for example, from optimization of transition rates. So the conclusion is that, okay, optimality of global observables may be similar to this information flow, can come at least partly from noise-induced behavior. So instead of saying that evolution is doing all the optimizing, you can reduce the explanatory burden, which of course is rarely paid back. You never actually see what evolution is doing. And a lot of the optimization can just come from the fact that you have noise-induced behavior that has this built-in optimization there. And although that's a very qualitative statement, very, very loose, it does have predictions. So it predicts that the distance to optimality that was measured will decrease if the noise decreases, and that can be tested in principle. So overall, the way to think about these things is that it's a bit similar to the way that I teach the second law in my thermodynamics course, that the way to understand that the second law in the end is that we tend to see the most likely states. But instead of applying that to statics, to the probabilities of individual states, this is really now a statement about dynamics. We tend to see the most likely trajectories, okay? And that's essentially what I'm telling you about. Okay, and another way to think about about optimizing global observables is that they're like distributed control problems, because we have control problems specifying optimizing individual hops. But then if I ask about some global observable, it will depend in general on all those hops. And I want to point out, okay, this is distributed control is another branch of control theory. There's lots of deep results there. I just want to point out there are non-trivial cases where decentralized control problems can be solved by local solutions. And now I'll actually give you an example from economics. So the so-called first fundamental theorem of welfare economics that came from the 50s says if you have a market economy with rational agents and a bunch of other conditions, then you can maximize global utility by each agent behaving rationally. So each agent is maximizing their utility, spending within their budget, and you can achieve a global solution where all the market's clear, so supply equals demand and so on. So this was, of course, used to motivate why we need some market dynamics and so on. But from the mathematical point of view, it's a static distributed control problem where the state is specified by the consumption of the consumers and the production of the firms, and the control is by the prices. So the prices in the end can find this optimal control where you get an efficient market. So if we apply this very loosely to noise control duality, it suggests a mechanism by which biological systems can exhibit market-like behavior. And the reason why I bring this up is because, as I was saying, on long-time dynamics, you get this emergent agential behavior. Now, what is that good for? Well, what that is good for is for economic type behavior, where you start to have agents behaving with their own individual goals, which may or may not be in conflict with each other. And this is the kind of thing that you can start to find possible and explain from a say principal point of view, and not just model phenomenologically. Okay. So at this point, let me present some conclusions. So stochastic systems have a control theoretic interpretation, and it's, I think of as a Rosetta Stone between mechanics and agency. What it tells you is that goal-directed behavior appears on long timescales, essentially for free, and as soon as you have multiple attractors. And this can justify agential descriptions of stochastic resonance and Brownian motors, and presumably lots of other behavior in biology that builds on those simple ingredients as the kind of building blocks of agency. Okay. So I think it's fair to say then that agency is really part of nature, if you look at it in this way. And as I also explained, then control is really paid for in time. It emerges over timescales. If we look at how these local optimizations relate to global ones, we may start to understand why biological systems optimize things like information flow. I mean, there's a lot more to do, but I think that's very promising. And in general, it suggests a picture of the cell as a system under persistent endogenous control, so that instead of everything working in spite of thermal fluctuation, that's only half the story. That say, when you're in one attractor, you have to be stable to the fluctuations pushing you around. But you also get, on long time scale, these hops that can have a functional role, and they solve these non-trivial optimization problems. Okay, so I'll end there. Let me just thank my collaborators on theory for reaction networks, Camille Scallier at ENS Paris, Masanari Shimada, who's now at Toyota Research, and Pega Beyrad is my postdoc. My colleague, Aidan Brown, who teaches me biology, and the funders here. So I'll just mention all of this is based on this archive paper. The current version is written in a very abbreviated form for physicists. I'm actually expanding it to a full-length article, and I will be replacing that one probably this week. So with that, let me thank you for your attention. And again, thank Quantum for the invitation. Thank you.